Here's a really interesting physics problem, and goes into how space can warp. But if you were more logical, how would you say that a galaxy traveling in that direction and you traveling the opposite direction at more than half the speed of light, how would light from that object ever encounter you? Now, before you start thinking space is warping and all that, and see, so if light encounters a third body, say off to the side in between these two, and if we are, say, imagine ourselves standing still relative to the observer, that other body is traveling in the opposite direction quicker than the speed of light. Except neither are breaking the laws of physics. Nobody's breaking the laws of physics here. And in the light clock relative to the observer watching the train, and how a pulse from here versus a pulse from here encounter the observer at the same time, relative to the angle, say, to their distance and stuff, how do they, if they could be emitted at the exact same moment, they will still take the same amount of time to reach the observer. And so in this video, they're mentioning Hubble spots as objects traveling faster than the speed of light. Well, no, it's just a compilement of two objects traveling in opposite directions. However, when a photon is emitted from that object, and it is pulsed backwards at the speed of light, well, you are only traveling at half the speed of light, so it'll still reach you. And I'm going to kind of go into my subquantum orbitals, and this is what I was going to expand on in my notebook for my gravitational field model. But the bottom part is explaining like this, and how a spinning photon maintains a constant speed that it spins quicker the sharper the angle that it has to curve around a gravitational field to maintain its velocity and energy without. So in theory, I mean, you curve around a gravitational field, it's actually getting more energy the sharper it has to curve, and there are other reasons for that on the average of a quantum pulse, the atmospheric pulse of electron atmosphere, but electrostatic field. And so that's why objects can move quicker away from one another than the speed of light. However, a light pulse from that object can still reach you, because at the moment it's emitted, it resets that relative point from the observer, which is you on this planet that's traveling only half the speed of light in the opposite direction, and that pulse is then traveling quick 2 times your speed. So, and then I guess, you know, when you look at it like what's happening at CERN, and how they can go 99.99. I didn't realize they were getting that close. That's really impressive and cool. But that's, so two particles are coming at each other quicker than the speed of light, right? Technically. Of course, they're not traveling quicker than the speed of light, because they still have to travel, say, from point A to point C, at point B in the middle to meet. They can't break the laws of velocity. So, and that allows them to demonstrate what would happen if we could travel at the speed of light, is that we are breaking all those barriers, the Coulomb barrier, all the, excuse me, and so they explode, right? Particles explode. Well, traveling at the speed of light, everything evaporates and disintegrates. This is going to be a shorter video than I thought it'd be. All the other ones I make, I'm like rambling because I have so much to say, but this is really quite simple to explain. Did anybody else explain it? No. But in the video here, they start talking about warp drives.
Somehow violating one of the universe's most fundamental
laws. So funny.
It could traverse the cosmos.
I think they do this to give us stuff to think about. That's what I think. So
it could traverse the cosmos in hours.
So warp drive, like, how can you warp space, which is basically gravity, which is like manipulating the electrostatic impulse to create a larger charge, and then still allow the particles of all this matter to not evaporate and basically do what happens at CERN, except not as explosive. So if you were to just match the speed of light right at the moment two particles at CERN interact or meet at one point at their vector or whatever, they come in, they're not going to fuse. They might pass through one. No, they wouldn't do that. But they're still not going to. Yeah, they might pass right by one another. But what am I trying to say? The evaporation of the particle fields is still going to be it's not going to be as violent.
So it looks like the spacecraft would ride a wave towards the destination star faster than light.
I cannot wrap my head around how these people think.
Very similar to the light given off by a galaxy.
Warp drives do not make any sense to me at all.
Than the speed of light. But warp technology is well beyond humanity's current.
Like a wormhole, like the standard theory of wormholes is folding 2 points and then connecting them. You're still going to have to move that matter all that distance to get to there. That's going to have to come halfway. You are going to have to come halfway to close that distance. And then you know how much energy that would take to move a planet? Fold space without destroying everything. And warp drives, like, what the hell are they talking about? I cannot, it's just not possible. I get what they're trying to say. They're creating an electrostatic, sort of like my gravitational field model at the back of the nucleus. The front is a lower energy density, higher energy density that envelops the craft and then pushes and propels it forward. But as you reach the speed of light, all these particles are going to be doing that exact same thing, less density, which means they can expand outwardly. There has to be a compensating field charge radiating towards the object to compensate for that frontal barrier to maintain the structure of the particle, which then it slows it down and it creates resistance. Otherwise, it'll just evaporate. Turn into colored glass condensate, right? Yeah, 10 minutes is good enough.